My topic was the image simulation and the schematic pipeline of this mission, but it turns out the topic is somewhat too broad. So I decided to just assume that the image simulation and the pipeline is already there, and I'm not going into all the details how I do these things, but just share some experience when we developed the F2 mission about how we know and struggle against some of the noise. So I will just start with this. So you have already seen this from Schroeder's talk. So this upside down is our microlensing telescope, and I just want to emphasize that the pixel size is 0.4 arcsecond, and the instrumental PSF 0.6 arcsecond, so that PSF is undersampled. And so the core science or the thing we optimize is to finding free floating planets, especially free floating Earth. So the science goal is very clear, but the problem is how we translate this science goal into the requirements of the telescope and the hardware design. Okay, so to do this, we need to do this end-to-end simulation. So it's basically logic flow is like this. So we input some design parameters and we use these parameters to simulate images. And then we do the photometry on these simulated images to get the photometric precision. And then based on that, we basically know how the noise are correlated with all the input parameters, designs. And we just adjust our error budget and as well as software. And also this will be iterated with the engineering team. So this is basically what our image simulation have been included. So we include actual PSF and the satellite jitter, many of the detected effects and optical decay, and as well as cosmic rays. So this is example of the simulated images. So you can see, indeed, the blending is very is the situation. So yeah, the field is very clouded. And for the photometric pipeline, well, it's still very preliminary, but basically we use effective PSF method that was introduced by Jay yesterday. And we are doing this PSF measure using every single images. And in each image, we basically have 4,000 bright stars. And we assume a perfect input catalog down to maybe 22 magnitudes. So this will basically be true until the ET launch. So this is again the basic procedure. So you can see this is the simulated image and the reconstructed PSF from the image. And this cross represents an example 18 magnitude star. So we basically do the photometry on a series of exposures. And we can then measure the Rmax of the flux, okay, and also the signal of this flux. So we basically find the Rmax is 317 electrons. And the signal is something like this. So basically, we know the signal to noise ratio of this example star. So this provides a point on this signal to noise ratio curve. So the star is here. So by doing this for all the stars in this field, we can have well, you can see each point, each black point here is a star. And we can finally get the sigma clip, the median value. This is our signal to noise ratio curve. And using this curve, we can simulate the light curves based on noise level and finally get the science output, expected science output. And then we basically optimize the final science output by the number of free floating Earths. Okay, so for the noise, in included in the whole mission. A lot of them. So of course I cannot talk about all of them. So today I just want to explain two examples. The first is charge diffusion, or also known as the bright effect effect, and the other is the telescope jitter. So I will start with the jitter effect. So the effect of jitter, it means that even in space, the telescope is not, the pointing is not static. So it has some jitter because of the thermal and mechanical oscillations. So if the jitter is something like nearly Gaussian, so that means the jitter between the pointing between two times are basically uncorrelated. So so this is basically a spectrum of this jitter. So if the jitter is something like this, it's fine. So we can get a signal to noise ratio like this, because we just expand the PSF a bit, but acts symmetrically. And it doesn't break the consistency between different exposures. But in reality, the jitter doesn't look like that. So this is a real jitter spectrum from TESS satellite. So you can see the jitter. Well, the power spectrum peaks at about 1 minute, and our Earth-2 is trying to get 10 minutes integration time. So it's affected, but well, strongly affected. So and this is the jitter trajectory. So you can see it's of course correlated with time. So under this trajectory, here I show how the integrated PSF affected by this. Okay, so you can see the PSF becomes irregular under this kind of jitter, and also PSFs of two different exposures will be significantly different. So so this is showing the signal to noise ratio curve of a Gaussian-like jitter and a TESS-like jitter. So well, I have to say that in both cases, the 1 sigma of level of these two different jitter scenario is the same. It's 0.15 arcsecond, but you can see the signal to noise ratio is quite different. So for the bright stars, it's it is more than 20% noisier. And also because we construct the PSF use these bright stars, so it also affect these faint stars. So the conclusion is that the jitter must be carefully considered, otherwise our output would be significantly overestimated. So finally, we basically set this value as our the highest acceptable value. And the second phenomenon, second fact I want to say is about the charge diffusion. So this actually induces two different physical mechanisms. So here I show you a sketch of the CMOS detector. So you can see this is basically a pixel. So 3 pixels. So the photon comes from the lower and hit this silicon and produce photoelectrons. And you can see that these pixels are not physically separated. So there are just potential wells between them, and it's not infinitely deep. So it's natural that the electron produced here can be end up with another pixel. So this basically produce this kind of electron diffusion. And this is not the only mechanism. And the other one is if one pixel have already accrued many electrons, so you will change this magnetic field, or not electronic field. So basically, so this pixel will be less attractive to other electrons, the following electrons. So effectively, it makes the pixel boundary smaller, the pixel size smaller. And also for infrared or the red sensitive detectors, so they always have thicker pixels because they want to maximize the quantum efficiency. So both effects will be stronger. So, but to some degree, this effect can be measured by a pixel-to-pixel correlation and using flat field images. So here I show the measured correlation matrix of both optical CMOS and our, well, not necessarily near infrared, but to some degree, red sensitive CMOS. So you can see these two are quite different. So this is the correlation matrix and the PSF after the distribution, and as well as the PSF size increase ratio as a function of the flux. So optical CMOS is basically fine, but for our red sensitive CMOS, it's increased significantly. So we also take this into account in our image simulation. So you can see for a long exposure, we use the red sensitive CMOS. And these two lines represent, one is the constant diffusion. It means only consider the diffusion is not flux dependent. And this one is the flux dependent diffusion. You can see if the diffusion is flux dependent, the simultaneous ratio is lowered a lot. So there are a few possible solutions. So the first is we can use a flux dependent PSF model. Well, to some degree, this relation between faint PSF and bright PSF is known because we have already measured the relation matrix. But we now just try an easier way, that is just to use many short exposures to shrink the dynamic range of all the stars, and that makes the difference between the PSF smaller. So we tried this. So this is basically what we have got. So the brighter stars are much better, but you can see the brightest stars are still worse, but it's fine because these, well, there are not many so bright stars, and they actually don't contribute a lot of the science output. So this is basically what we end up now. So we have 5 sigma at 25.5 magnitude and 80 sigma at bright stars. So then CKI will simulate cycles based on this noise curve to estimate like how many threshold planets we will detect and also measure their mass. And this is the output as a function of magnitude, the source magnitude, and after they magnify magnitude. Okay, so basically we finally have this number, 25 Earth mass floating planets in a 4-year mission. So I will just summarize my talk here. So first, the end-to-end assimilation is necessary to complete all these telescope design. And so we found basically 2 very important effects. So the first, the jitter and the spectral effect simultaneous a lot, and the trial distribution or bright factor effect also affect a lot, but they, to some degree, they can be correlated or modeled or suppressed. And finally, we have this output. So, and remember that our photometric pipeline is just a preliminary one, so potentially it can be much better in the future. So, thank you.
That's, the estimate is 45 free-floating Earths with mass function. You're using distributed mass function. There's a couple of them. One with a broken power law that basically avoids a huge number of very stubborn mass planets.
Yeah. So we basically assume the TACAS.
So the single power law?
Yes, single power law, and well, assuming 2023 and go to 2022 are basically consistent with this.
25 is the mass measurement, right?
Yes.
So how many you expect if you relax the requirement without the mass measurement?
Without mass measurement is about a factor of 2 more.
The 2.
Yes. So we basically have half.
It's very relatively high efficiency to get the measurement.
Yeah. Yes.
Got a quick question, which is for the jitter, is there any option on board to stack images, say stack shorter exposure images a bit lower one and that kind of help reduce that effect?
Well, I have to say, because thermal resources on board is not very good, so we will just do average of minutes.